And they're based on a engineering design called Crossflow filtration. Conventional filtration, cartridge filters, media filters that we're all familiar with, is a batch process. The 100% of what you want to treat in the way of a contaminated water supply flows through this medium, whatever it is, and hopefully everything you want to remove is left behind on the surface. It's a batch process. Once this gets so full of whatever you're trying to remove, you have to take the system offline and regenerate it or throw it away if it's a cartridge or something like that. But it's treated as a batch process. On the other hand, the membrane technologies almost completely are based on cross-flow filtration. You have one stream coming in, carrying the contaminants you want to remove. This whole system is under pressure. So the pressure forces some of the purified, if you want to call it that, water through the medium, and this becomes the treated water. The stream that contains the contaminants you've removed exits as a concentrate stream. Theoretically, this never has to be regenerated. In reality, it does have to be cleaned, but it's a continuous process, and ideally, if somebody wants to build a reverse osmosis system, for example, they try to build it so that the cleaning takes place about once every 3 months. So it's certainly much more continuous than a batch filtration process. And there are 4 basic membrane processes today. Microfiltration, which involves some of the membrologists refer to differentiate between these 4 technologies based on pore size. I would rather use the function to distinguish one from another. The function of microfiltration is the removal of suspended solids. I don't care whether they're large suspended solids or submicron down into the colloidal size. If the technology is used to remove suspended solids, it's microfiltration. And here you have the water moving through, salts moving through, macromolecules, which is another way of saying organic contaminants, also pass through, but suspended solids are in particular rejected or held back. Ultrafiltration is basically a larger sized microfiltration membrane, a larger pored MF membrane. And that, as you can see here, the water goes through, salts will go through, but both macromolecules and suspended solids are held back. So both microfiltration and ultrafiltration are based on pore sizes. It's a sieving technology. What's too big to go through the pore won't go through the pore. It's as simple as that. So you can get close to 100% removal if you have the right pore-sized membrane treating a particular contaminated water supply. Nanofiltration is a loose RO, and this has become a field in itself, in that there are now the manufacturers are making specifically nanofiltration membranes. In the early days, a nanofiltration membrane was a reverse osmosis membrane that failed quality control. Basically as simple as that. But nanofiltration is, as I said, it's an RO membrane that doesn't remove to the same degree, remove salts to the same degree as an RO, a good quality RO membrane will, but it removes salts based on their valence. Multivalent salts, such as calcium and magnesium, the hardness ions we have in water, are specifically rejected by an NF membrane, whereas the monovalent salts, such as sodium, which is the other most common cation in raw water supplies, will pass through relatively easily. So an NF membrane, and their first application was as a municipal softening membrane. It would specifically reject the hardness ions and yet allow the sodium ion to go through. You might say, well, why? What's the sense of doing that? Well, the fact is it uses less energy, is a less expensive process than reverse osmosis. If you're treating municipal water for a drinking water supply, in most cases, unless it's a seawater application, in most cases you don't really need the rejection capabilities of RO, but you can soften it with NF, nanofiltration. And reverse osmosis, which is the, quote, ultimate. This will reject salts, oops, I'm sorry. It will reject salts, macromolecules, and suspended solids. And reverse osmosis and nanofiltration reject based on a percentage. They are not 100% effective. There is no RO membrane that will remove 100% of the salts, period. Now, we've got some pretty damn good membranes out there now, 99.8% rejection of salts, but it's not 100%. So there is some passage through even the tightest RO membrane, but they're still extremely effective. And this is kind of a summary of how they fit in there. Microfiltration, removing the suspended solids, ultrafiltration, removing the dissolved macromolecules, nanofiltration, removing the divalent salts, and reverse osmosis, removing the all of the salts. And of course, they'll also remove anything that's larger than what their capabilities are. But then it's a matter of cost. And here's a chart. I don't want to dwell on this. It's in the PowerPoint and it's in the paper. A chart comparing the four membrane technologies with regard to a number of parameters. And it just provides a comparison. And the issue is, once you have selected the membrane, the membrane technology you want to use, now you have to package the membrane into a reasonable device or element, as it is called in the industry. And the one that, those of you who are familiar with membrane technology, you're probably most familiar with spiral wound membranes. Spiral wound membranes were invented in the United States in about 1960. There are 6 manufacturers in the US. 5 of them are basic manufacturers. In other words, they manufacture the membrane, they roll it into the spiral element and sell it as such, and they're based here in the US. There are now getting to be a few more manufacturers overseas in China and South Korea. But still, the basis of the spiral wound industry is the US. And because they're all made to compete with each other, they are far and away the least expensive reverse osmosis membrane configurations or devices. Spirals are. They're not the most effective in terms of performance. And if you're getting into water reuse, for example, like gray water reuse or black water or one of those applications, you must pre-treat them. Fortunately, you can pre-treat them with another membrane. But for wastewater applications, spirals are very prone to fouling, plugging, which is the bane of all membrane technology. So, although they're the least expensive, they also are the most susceptible to fouling. Tubular membranes are just like that. They're tubes. They normally range from 1/4 to 1/2 inch ID. Normally, the feed goes in the interior or the lumen of the tube. The membrane is coated on the inside, and the permeate under pressure comes out through the wall and is collected.